In this video, we're going to find the power absorbed by a resistance, a certain resistance, which we're going to call, I don't know, like R1, and also the voltage between 2 points. So the circuit this time is going to be the following one. We're going to have a voltage generator. We're going to have a resistance here. Then we're going to have a certain node, which we're going to call A. We're going to have a resistance here. And then another node, which we're going to call B. And on the top here, I'm going to have another resistance and a current generator pointing up in this direction. And then we're going to have this other resistance and another resistance here and current generator here, which we're gonna call J later on, and this one, another generator of current. There we go. Everything is connected down here, and this one is gonna be my point C. So I'm gonna call the voltage generator V1, the resistance here R1, this one is gonna be R2, this one is gonna be R5, and then we have R3 and R4. This generator is gonna be J2, this one is gonna be J4, J5, and I'm also gonna say that the current flowing here is gonna be called I1, and the current flowing here, we're gonna call this I3. Okay, so the problem is saying for the circuit on the left, we know V1 equal to 12 volts, Ji equal to I amperes, Ri equal to I ohm. Find the power absorbed by the resistance R1 and the voltage VAC. Okay, so first thing first, well, by Ji basically means that this one is 2 amperes, this one is going to be 5 amperes, this one is going to be 4 amperes, and Ri is like always, so this is going to be 1 ohm, 2 ohm, 5 ohm, and so on. So let's just write it next to it. So we know that the voltage is 12 volt. This one is 2 amperes, this one is 5 amperes. This one is 4 amperes, and then the resistance is this one is going to be 1 ohm, this one is going to be 3 ohm, this one is going to be 2 ohms, this one is 5 ohm, and lastly this one is 4 ohm. Okay, so as I said, first thing first, the idea is to get the node which we just call B. Okay, so this node here, and I'm basically going to be applying the Kirchhoff current law to the node B. So apply the Kirchhoff current law to the node B. Okay, so Kirchhoff current law basically says that the sum of all the current entering a node is equal to the sum of all the current going out from that node. Okay, which can also be stated as the current meeting at a node, the sum of the current meeting at a node is 0. So in this case, we have entering the node, we have I3, okay, which is gonna get into the node. Now we're gonna have J2 because this generator of current is getting into the node. Then we're gonna have J4 going out from the node, and also J5 is still gonna get into the node. Okay, so basically let's just say, okay, the sum of all the currents entering a node is equal to the sum of the current going out from that node. So entering the node we have I3 plus J2, okay, because he's pointing in this direction, so he's entering the node, which I circle in green. So plus J2 plus J5, because it's going up and then it's gonna go turn left and get into the node, so plus J5 equal the only one who is leaving the node, J4. So those three guys are gonna be equal to J4. Now what we're interested in is actually I3, so this current here. So I can just rewrite everything in terms of I3, so I'm just gonna bring those guys on the right. So I3 is going to be equal to J4 minus J2 minus J5. So if we just plug numbers back into this, J4 is 4 amperes, J2 is 2 amperes, and J5 is 5 amperes. So we have 4 minus 2 minus 5. So I3 is actually negative 3 amps. Now, I'm going to do the same, but for node A this time. Whoops. Okay. So I'm going to do the same, but for node A. There we go. This is going to be my node A. So I'm going to apply the Kirchhoff current law to the node A. So at the node A, we're going to have, well, as I said, as always, the sum of all the currents entering a node is going to be equal to the sum of all the currents going out from that node. So entering in a node, we have I1. Then we're going to have J4, because it was going to go out from the node B, so passing through the resistance and getting into node A, so plus J4. And all these, those two are going to be equal to the one leaving the node, so going out from the node, which is I3, which we have just found. So those two guys are going to be equal to I3. So now I can write everything in terms of I1, so I can just bring J4 on the right side. So I1 is just going to be I3 minus J4. And if I plug numbers back into this, I will get I3, which we have just found, so it's negative 3, minus J4, which was just 4 amperes, so minus 4. Therefore, I1 is equal to negative 7 ampere. Now, the absorbed power, the problem is actually asking us the power absorbed by the resistance R1. So this resistance here, okay? In order to find the power absorbed by that resistance, I can basically say that I'm just gonna call it PR1, okay, the power absorbed. Just gonna call this, yeah, PR1. I'm gonna say, okay, this is gonna be equal to R1, so the resistance itself, of course, times I1 squared that we have just found. So PR1 is just 1 ohm, so 1 times I1 squared, so negative 7 squared. So PR1 is actually 1 times 7 times 7 is 49. So PR1 is 49 times 1, which is 49 watts. And this is the power absorbed. Now we have just found the power absorbed by the resistance R1. We only have to find the voltage VAC. So the voltage V between the points A and C, those 2 points here. So we can actually say, okay, we can use again this. Notice this is A, this is C. What do you actually see? What are you thinking about? I mean, you're gonna see it because I'm gonna be doing it in just a moment. But what are you thinking about? We just used the Kirchhoff current law 2 times for those nodes, but this one is actually a closed loop. So closed loop, does it remind you something? Of course it does. If I consider this whole thing as my closed loop, I can use Kirchhoff voltage law. So if I use the Kirchhoff voltage law, I can say that the sum of all this is going to be equal to 0. So I can say that V1 minus R1 times I1 minus VAC is going to be equal to 0. And therefore, VAC is going to be equal to V1 minus R1 times I1. So VAC is actually going to be equal to 12 minus 1 times negative 7, which is just VAB equal to, well, 12 plus 7, because negative 1 times negative 7 give me a positive. Negative times negative. So 17, 18, 19. So 19 volt is oh, well, why did I write VAB instead of, yeah, it's, I just meant VAC, of course. So VAC is just going to be 19 volt. And we have just found the second part of the problem. So yeah, this is pretty much it for this problem.